Hi class, let's try this. This is my umpteenth attempt at recording this. So let's see if it works. This molarity. We're going to talk about concentration and what how we use concentration in chemistry. We're going to describe the fundamental properties of solutions, calculate solution concentrations using molarity, and perform dilution calculations using the dilution equation. In the preceding sections, we focused on the composition of pure substances. However, mixtures, samples of matter containing two or more substances physically combined, are more commonly encountered in nature than are pure substances. Similar to a pure substance, the relative compositions of a mixture plays an important role in determining its properties. So we oftentimes have reagents on the shelf that are in solutions instead of as pure substances. Okay, this is just saying that the sweetness of coffee depends on the concentration of sugar. Solutions occur frequently in nature. Solutions are another term used for homogeneous mixture, uniform composition, and properties throughout its entire volume. The relative amount of a given solution component is known as its concentration. A solution consists of two components: the solvent, the component with a concentration that's significantly greater than all other components, and the solute, the component that is typically present at a much lower concentration than the solvent. A solution in water is, a solution in which water is the solvent is called an aqueous solution. Molarity is the number of moles of solute in 1 liter of the solution. So molarity is equal to moles per liter. Molarity is a useful concentration for many applications in chemistry. If we have a soft drink like Sprite or Coca-Cola, it typically contains 0.133 moles of sucrose. Its molar concentration of sucrose is therefore 0.133 divided by 355 milliliters, which is 12 ounces, but it has to be converted into liters so we get this in molarity. So moles per liter gives us 0.375 molar. This is just another example of a solution. Acetic acid, I'll tell you right now, it's typically found in the units of percent by weight, and it's 5% vinegar and water. Anyway, dilution is the process whereby the concentration of a solution is lessened by the addition of a solvent. Okay, so if you have lemonade that's too strong, you add more water to it, and you've diluted it. Dilution is a common means of preparing solutions of a desired concentration. By adding solvent to a measured portion of a more concentrated stock solution, we can achieve a particular concentration. So in this case, the stock solution might have been this copper nitrate solution at this higher concentration, and that same amount is put over here and diluted by 1/2 with water. So this tube and this tube contain the same amount of copper nitrate. It's just this one is more dilute, and therefore it has a larger volume. Which brings us to the dilution equation. They've made an unfortunate choice of variables here. We're going to call concentration C and volume V. In this case, they are using the units associated with concentration, which is molarity, and liters for volume. But the number of moles, if you have the concentration, is the concentration times the volume. It gives you the number of moles. In this case, this is molarity. And if you have case number 1 and case number 2, in the case of dilution, N1 and N2 are the same, and the first concentration and the first volume are going to equal the second concentration times the second volume. And that's the dilution equation, expressed here as C1V1 equals C2V2. Now this is true even when the concentration does not express moles. If it expresses mass, well, the mass is before and equal. The solute are the same, and this dilution equation still holds. But this is an important equation for us. If we know the volume and concentration we start with, and either our target concentration or volume, we can solve for the one unknown. For example, if we have this 0.85 liters of a 5 molar solution of copper nitrate, and we dilute it to a volume of 1.80 liters. Let's see, is that right? Okay, that's a little bit more than double. What is the molarity of the diluted solution? So it's going to be a little bit less than, it's a lot less than half. Anyway, that's the way it comes out. Oh, I'm sorry, it's a little bit less than half. 2.36 instead of 2.5. Anyway, we know C1 and V1, and we also know V2, and we can rearrange this so that all the knowns are on one side and allows us to calculate the unknown. In this case, the unknown C2. C2 is equal to the concentration 1 times the volume 1 divided by the volume 2, and it comes out to be 2.36 molar. Other units for solution concentrations. So we're going to look at mass percentage, volume percentage, parts per million, parts per billion. Molar concentration is useful for evaluating the concentration of solutions. In this section, we will introduce some other units of concentration that are commonly used in various applications. The mass percentage of a solution component is defined as the ratio of the component's mass to the solution's mass expressed as a percentage. So mass of the component, mass of solution times 100% gives you the mass percentage. We are generally most interested in the mass percentage of solutes, but it is also possible to compute the mass percentage of solvent, which of course, if you've only got one solute, then the mass percentage of solvent is 100% minus the mass percentage of that solute. Liquid bleach is an aqueous solution of sodium hypochlorite. This brand has a concentration of 7.4% of sodium hypochlorite by mass. If this happened to have a density the same as water, 1 gram per milliliter, then 1 liter of this, well, let's take that back. We'll say 1,000 grams of this. It therefore contains 7.4 0.074 times the 1,000 grams. It would therefore contain 74 grams of sodium hypochlorite. And so this is assuming we have an HCl solution. If we have its volume, we multiply by its density to get the mass of the solution, and then multiply it by its mass percentage to get the mass of the solute. The concentration of a solution formed by dissolving a liquid solute in a liquid solvent is often expressed as a volume percentage. Now you're going to see these volume percentages on alcoholic beverages, typically, like beer and whiskey. Beer is typically 5% by volume, they'll say on the label. And things like whiskey are Also percent by volume, but they give another term, proof, and proof is actually percent by volume times 2. The mass volume percent is a ratio of a solute's mass to the solute's volume as expressed as a percentage. Okay, so that would so this is like mass in grams per mass of grams, but in this case we're using milliliters instead of grams on the bottom, and then multiplying that by 100%. It's a real bastard units. Of course, we're not going to focus on it. The specific units used for solute mass and solute volume may vary depending on the solution. For example, physiological saline solution used to prepare intravenous fluids has a concentration of 0.9 mass per volume, indicating that it has 0.9 grams of solute per 100 milliliters of solution. Mixed mass volume units are commonly encountered in the medical setting. The sodium chloride solution is 0.9% mass per volume, and this device measures glucose levels in blood. The normal range is around 70 to 100 milligrams per deciliter. Very low solute concentrations are often expressed using appropriately small units such as parts per million or parts per billion. The mass-based definitions of parts per million and parts per billion are, you take the mass of solute divided by the mass of solution times a million in this case, and that gives you parts per million. Normally, this is for measuring very, very low concentrations, so the mass of the solution will essentially be it'll be almost pure water, unless you have massively high concentrations on the order of hundreds of thousands of parts per million. And the other is parts per billion. It's the mass of the solute divided by the mass of the solution times 1 billion, 10 to the 9th. And of course, 1 billion parts per billion would be wouldn't even be a solution, it would just be the mass of the solute. And that is essentially it. These parts per million, parts per billion are used to measure trace level concentrations of contaminants, which in this case could render unfiltered tap water unsafe for drinking and cooking, which can sometimes be remedied by inline water filters to reduce the concentration of solutes in the tap water. And that is the end of that. Let's get out. Let's get out and let's save.